Hello friends, in this video we are going to discuss how to run simple linear regression analysis with the help of R software. The simple linear regression analysis is used to predict the value of dependent vector based on certain independent vector, and both vectors should be numeric in nature. To understand the process, we open the dataset woman, which is inbuilt in the R software. So I type datasets and select the required dataset named as a woman. Alt plus enter. Now you can see the dataset in the console area. The data is all about a 15 women consisting certain height and weight, and we are going to predict the weight with respect to certain height. So in this way, height is our independent vector and weight is our dependent vector, and both vectors are numeric in nature. But before that, before run the simple linear regression analysis, we have to verify or we have to examine certain assumptions. The first assumption is that both the vectors should be numeric in nature. So we can see in the console area that height and weight, two vectors are there, and the both vector consist numeric element. So the first assumption is verified. The second assumption is both vectors should be linear associated to each other. Once this assumption is met, then only we can run the simple linear regression analysis, because there is a one condition that both the vectors should be linear associated to each other. To examine this one, we create or we prepare the scatter plot, and then we'll assume whether both vectors are linear associated or not. And we also compute the correlation coefficient between both the vectors. So we use correlation coefficient. So I'm using the function core, and this is my parent dataset woman. I use the $sign and select the height. Again, this is a parent dataset woman. Use $sign and then select weight. And once you Alt plus enter, you can see the correlation coefficient is plus 0.99. It means both the vectors, these are a very strong associated to each other, and both the vectors are positive in nature. Now let us plot a scatter diagram to verify whether they are linear associated or not. So I'm using the function plot and using the same vector, and now you can use Alt plus enter. So you can see in the plot area, this is the direction is upward, and so this is a strong positive association between both the vectors, and these are linear associated to each other because we can see a one straight line which is in the upward direction. So this assumption is met that both the variables should be linear associated to each other. Now I'm using the command to run the simple linear regression analysis. So for that, I develop the object regression1, and I'm using the command lm. So lm stands for linear model, because there's a one assumption that you can run the simple linear regression once both vectors should be linear associated. So I'm using the command lm, and now the first vector is height. So always remember, the first vector represents the dependent vector, and subsequent vectors that they represent the independent vector. So in this case, the height depends on weight. In this case, the weight depends on height. So weight is your dependent vector and the height is independent vector. So I type woman $weight, use the sign of tilt, and then parent file name woman and height. Now Alt plus enter. Now you type regression1, that is our model. Alt plus enter. Now you can see certain specifications which are coming in the console area, that is coefficients, intercept minus 87.52, and woman height is 3.45. Now what they do represent, intercept means the constant, and this is woman height 3.45, that represents the coefficient of a independent vector. Now what does it mean? It means that if we make 1 unit change, in the height, the weight will be increased by 3.45 units, because this 3.45 is positive in nature, so we can say that there is a positive association between both the vectors. And so with this regression 1, we can develop a one regression equation, that is y equals to a plus bx. So in this case, y is weight equals to a, the constant is 87.52, and this is coefficient of independent variable, that is small b. This is positive, so this is 3.45 multiplied by height. So now if you put any value of the height, you can find the respective weight. So in this way, the regression equation y equals to a plus bx is used to predict the value of the weight with respective height. So in this way, we can use it regression model for the prediction. Now the next command, I can use summary and then regression 1. So instead of this constant and the coefficient of the independent vector, we can have much more detail related to the regression model. So let us find this one. Now I'm going to press Alt plus Enter, and in the console area you will be having a various specifications which you can see. Now what are these specifications? The first one is the residuals. So now what is the meaning of the residuals? Residuals are the difference between the observed value and the predicted value. Because once we run the regression 1, this is our model regression 1, so the R predict all the specifications of the 15 women, and because this is based on the prediction, so there is always chance of a difference between the observed value and the predicted value. So this difference is called residual. Now we can see the minimum value of the residual is minus 1.7, and the maximum difference between the observed and the predicted weight is 3.1. Along with that, you can easily see the first quartile value is minus 1.1, the third quartile value it is 0.7, and the median is minus 0.3. So friends, you have to find out these values of the residual. If the residuals values are very high, it means the regression model is less powerful. Or in the other way, if the residuals value are very low, then we can say that our regression model is good enough to predict the value of dependent vector. Now the second, the R gives us the results of various coefficients. In this, intercept minus 87.5, which we already computed. Along with that, you can find out independent vector height with its coefficient 3.45, which we already computed. Along with that, the p-value of this independent vector comes 37.85, and the last column, this is PR, that is 1.09 e raised to power minus 14. So if we solve this one, 1.09 e raised to power minus 14, that will be 0.000. So 1.09 divided by 110 times 14, 1, and 14 times 0, so that will be minus 0.000. So now what does it represents? This value represents whether your independent vector significantly affect the dependent vector or not. So you have to always consider that this value, this p value, should be less than 0.05. Why 0.05? Because this R software by default, it is set at 5% level of significance. So if it is less than 0.05, then you can say that the height or your independent vector significantly affect your dependent vector. So now in our case, this value is less than 0.05, so we can say that the vector height is significantly affect the independent vector weight. And second, you can see these three stars are there, so that indicates that this is the significant. So in this summary, first you will be having an idea of the residual values, and second you have to find out what is the value of constant or intercept, what is the value of coefficient of independent vector. Now both these intercept and coefficient of an independent vector, they are used to predict the dependent vector by drawing the regression equation. So in this way this is your regression equation which you can use, and you can predict the value of dependent vector. Along with that, the coefficients, these gives the result of the t-value along with probabilistic features. So if the p-value, in short, probabilistic value it is called p-value. So if the p-value is less than 0.05 in your model, so you can say that your independent vector significantly affect your dependent vector. And the last one is your multiple r squared value. This is 0.99. If you multiply with this 0.99 into 100, this is 99%. It means your independent vector contributes 99% variance in the dependent vector, or in the other words you can say the height contributes 99% of the variance in the weight in the regression model, which is good enough for prediction. And the last one is your F statistics, which stands for the ANOVA results, that indicates it p-value also less than 0.05. So it also indicates that your regression model is significantly better, significantly improved as compared to the baseline model. So in this way you can run your simple regression analysis with these assumptions, with these results. So first you have to find out the correlation. Second, you have to verify some sort of the assumption, whether the vectors are independent, whether the vectors are linear associated or not. So we can find this with the diagram of scatter plot, and then you have to run the regression model. Based on this regression model, you have to draw the regression equation based on the intercept or the value of constant and the value of coefficient of independent vector. And then at last you are required to verify, or you are required to run the summary function. Summary function gives you the three results: the value of the residuals. The value of the residuals should be the minimum residuals, that indicates a better regression model. Second, it also gives you the coefficients. It means the value of intercept or constant, the value of coefficient of independent vector, along with that the t-value of the independent vector and associated p-value. So this value should be less than 0.05, and at last the F statistics related to the ANOVA, that should be the less than 0.05. And multiple r squared value, that indicates that how much proportion in the dependent variable is contributed or accounted by the independent vector. So this is all about simple regression analysis, and in the description box I have given you one question for the practice. So identify the relevant vector based on that particular situation, and then run the simple linear regression analysis and give the answers for as mentioned in the description box. Thank you so much.